Comment 870 is about an example of where the way we solve equations is actually flawed. It doesn't always work. I'll just give you a quick example. Normally we tell you that we can do the same thing to both sides, informally referred to as red dudes. And that's generally true. So if 8 is equal to 8, then it'll still be equal when we divide by 2. The flaw, though, is that sometimes something false can be rescued by a particular red dude. So negative 3 doesn't equal 3, but when you square both sides, it does become equal. So therefore, we do need to be careful whenever we're using our ordinary algebraic machinery to solve equations. And comment 870 is about exactly that situation. Now, the specifics of it for this particular comment are the following. So I'm going to show you an example of a method that gives you solutions to equations when you have modulus symbols around something. So, for example, x minus 1, all modulus, equals, let's say, 2x. Now, the algebraic method is to do the question twice. Once with the modulus bars completely left off, and again with the modulus bars, both characters replaced by 3 characters. In other words, these 3 characters, a negative and opening and closing brackets. So that's us doing the question twice. Once with these left off, another time with these replaced. And now you do your normal thing. So subtracting x from both sides here gives you x equals negative 1. Timesing both sides by negative 1 here gives me this. Adding 2x to both sides gives this. Adding 1 to both sides gives this. And dividing both sides by 3 gives you that. Now what comment 870 says to do is that you must check that both of these are genuinely solutions. Now there's 2 ways of doing that. One is just to substitute in and check that it's true. So this is me substituting into the original equation for x equals negative 1. And I get which is wrong. So in other words, that is not a solution. And let's check this one. And that one is the case. So the algebra produced 2 solutions, but only one is the case. There's one solution, x equals a third, the other one is not a solution. Now, substituting back into the equation is one option for checking that the algebra has given you correct solutions. The other option is what comment 870 tells you to do. It basically says draw a graph. So if you graph this, if it was just y equals x, it would be these fat dots. Y equals x minus 1 would be these crosses. And when you put modulus bars on it, everything that was down low becomes high. So that'd stay there, but this cross would become this circle, this cross would become this circle. And so what you get is this classic V shape. The graph of that is y equals 2x. That would be these made twice as high. So it's going to be these squares. those graphs only intersect once, and that is why there's only one solution. Now, and that solution, moreover, is a little bit more than 0, so x equals a third makes sense, and x equals -1 does not make sense. The reason why x equals -1 has come up is because if you leave the absolute value bars off, the modulus bars off, it's basically the same as continuing it down like that, and there is an intersection down there, but not for the actual graph, only for the algebra that the method produced. So basically, comment 870 says when you're solving certain types of equation, you need to draw a graph to check that the algebra solutions genuinely correspond to intersection points on the two graphs that you draw.